In the last screencast, we talked about neutralization reactions, and one of the things to be aware of is that a neutralization reaction may be used to determine the concentration of an unknown acid or base. And the method that we use to do this is called a titration. So a titration is just an analytical method to determine the concentration of a solute in a sample by reacting with a standard solution. And so when we talk about a standard solution, this is just a solution with a known concentration. And so generally how this works is you will have a flask here. So there's my friendly flask. And there's going to be some liquid in it here. And that liquid, you're going to have a known amount and an unknown concentration. Then you're going to have a burette here, or a dropper or something along those lines. And it's going to have like a little dial there, right? It's called a stopcock. And what you're going to do here is it's going to have different volumes here, and you are going to have some liquid inside of this. And this liquid will have a known concentration. And that's your standard solution, right? So it's going to be in the burette. And what you're going to do is you are going to add the thing in the burette to the thing in the Erlenmeyer flask, and it's going to be an acid-base reaction. And what's going to happen with an acid-base reaction, for example, if you are reacting HCl and NaOH, it'll react in a 1-to-1 ratio to form NaCl and water, okay? And if this is happening in the flask, eventually you're going to get to the point where here the pH equals 7 for this example, okay? That would be where what we would call the equivalence point, and that would happen when the moles of HCl and the moles of NaOH equal each other, okay? Now, not every equivalence point is at a pH of 7, but for this example it is. So the definition of an equivalence point is just the point when the moles of added titrant are stoichiometrically, so that word's popping up again. And remember, stoichiometrically just refers to the molar ratio that we see here equal to the moles of the substance being analyzed. So that means if we know 1 mole and we know they're equal, then the other mole has to be the same amount. Now, we use an indicator to show us where the equivalence point is. Okay, so an indicator is used to tell us when the endpoint is achieved. And so what do I mean by that? Well, this is called phenolphthalein. This is a really well-known indicator. And in an acidic solution, phenolphthalein is clear. And then when the solution changes from a pH of 7 to 9 here, it turns to pink. And so, for example, if we know these are here in a 1-to-1 mole ratio at pH 7, that's going to happen right where we go from the 7 to the 9. So it would happen right where we saw the pink. And so depending on what pH you have equivalents at, that depends on the indicator that you would use. Okay, and so this is an example of bromothiamyl blue, this is methyl red, and they go through and change between several different colors. Now, once you have reached where the color of the indicator changes, that's called the endpoint. And the endpoint here, and I'm going to try to block this off so we can really delineate it, is the point reached when the indicator changes color. Okay, so when we look at this, I want to show another example. This is another example. This is when phenolphthalein is added here. And so what you have here is an acid, okay, and it's got an unknown concentration. And in the burette here, and that's just the bottom part of the burette, you have a base, right, with a known concentration. You will add the base to the acid until it turns pink. And when it turns pink like this, you need to record the total volume of base used to reach the endpoint. All right, because that's the endpoint. And so what you can then do is you can use the base molarity or concentration and volume to figure out the moles that have reacted. And then once you figure out the moles that have reacted, you know there's 2 moles of NaOH for every 1 mole of H2SO4. You can come back here, right, and determine the concentration of H2SO4, okay? Now, we're going to go over this in class. I have a really nice foldable to help us with this, but different people learn in different ways. And so if this was really fantastic for you, then I hope it was. But I want to continue on with this example. So this is what you would do in the lab, right? You would add these 2 things together. It would turn pink. You would reach your endpoint. And so now you're going to calculate what your original concentration of H2SO4 was. And so to do this, you need a stoichiometric calculation. Now, the stoichiometry of the neutralization reaction is going to be 2 to 1. So in other words, right, we need 2 moles of NaOH to neutralize 1 mole of H2SO4. Now, we can write that, right, at the endpoint here, the number of moles of H2SO4 that we used is going to equal the number of moles of NaOH divided by 2, okay? And so that's a way that we can talk about that. We can also write this as a mole ratio that says, hey, look, for every 1 mole of, for every 2 moles of NaOH, you need 1 mole of H2SO4, right? Or for every 1 mole of H2SO4, you need 2 moles of NaOH to neutralize it. That's another way to say it. So I want us to actually do a problem. What's the concentration of sulfuric acid if 15 milliliters of it reacts with 18.45 milliliters of a 0.0973 molar NaOH solution? So here's the deal. This is how the question will be given to you, okay? And what I like to do first is to draw a diagram. So my first step is I'm going to draw a diagram because this helps keep me organized. And so I'm going to say, look, I know I'm going to have a flask here, and in this flask, right, is my 15 milliliters of sulfuric acid, and I don't know the concentration. So I don't know the molarity. Whatever you don't know the molarity of, it goes in the flask. Okay. Then in my burette here, right, I had NaOH, and I know I used 18.45 milliliters, and the concentration was 0.0973 molar. Okay. This just helps me organize. This helps me know what my information is. I can imagine the experiment I did in the lab. So you should do this experiment in lab. I can imagine the experiment I did in the lab, and I can organize where everything is. Now, I am going to start the calculation with the chemical species I have the molarity and volume for. Okay? Because what we're going to do is we're going to go from moles of NaOH to moles of H2SO4, and then we can use the volume to get us to the molarity of H2SO4, and molarity is a concentration unit, and so that's what we're looking for here. So to get to the moles of NaOH, I'm going to come here and I'm going to say, all right, I have the volume and molarity, and I remember from my molarity triangle, we got moles per liter gives us molarity. And I am trying to find my moles of NaOH. So I'm going to take my liters and multiply it by my molarity to give me that. And so I'm going to come here and I'm going to do this first step in blue, where I say, all right, I have 0.0937 moles of NaOH per liter of NaOH. I need to convert this to liters. So I take 18.45 milliliters, and I know there's 1,000 milliliters in a liter. And when I do that, that gives me 0.01845 liters. Okay. Now I'm going to try to keep my line kind of right here. So I can stop here and do this math, but I'm going to go ahead and do one more step. So we've gotten, this will give us our moles, because we can see here where our liters of NaOH cancel there. And now I'm going to come here to the second step, which I'm going to do in purple, okay? And I'm going to convert to moles of H2O. To do this, I need the mole ratio, Okay. And we looked at the mole ratio on the previous slide from the balanced equation, and I know there's 1 mole of H2SO4 for every 2 moles of NaOH. Now, that 2 moles of NaOH goes in the denominator because you want to cancel out the moles of NaOH there, and we're left with moles of H2SO4. Now, at this point, I do pick up my calculator and go ahead and work this out. And so when I work this out, I get 8.98 times 10 to the negative 4th moles of H2SO4. And then the third step, right, is where I calculate the concentration by dividing by the volume. So I'm going to take 8.98 times 10 to the negative 4th moles of H2SO4, and I'm going to divide by the volume of H2SO4, and it needs to be in liters because we're getting molarity here with concentration, and that's moles per liter. So when we do this math, that gives us 0.0598 moles per liter H2SO4. Now, I want you to pay attention, right, that the final answer here is in 3 significant figures, and that's because here we have 4 significant figures. Here we have 4 significant figures. But here we only have 3 significant figures. And so our answer here has 3 significant figures. All right, we're going to do more of this in class. Like I said, I'm going to have a handout for you. And we should, we'll talk more about this and do some more examples. If you have any questions, as always, please feel free to stop by my office.